Section 4.7 uses isosceles and equilateral triangles. So to start off with an isosceles triangle, we have to look at some terms. Now an isosceles triangle is a triangle with two congruent sides. So let's assume that these are our two congruent sides. Now the legs of those triangles are in fact the two congruent sides that we have. So we could call these both the legs. The base is going to be the non-congruent side. This would be the base down here. The base angles are going to be the angles opposite the legs or adjacent to the base. So that means the base angles would be these two right here. Now we'll give the third angle a title, and that would be the vertex angle. We're not going to do much with it, but it may come up as a vocabulary word, so that is the vertex angle. Now why we need the base angles is because we have the base angles theorem, which tells us if two sides of a triangle are congruent, then the angles opposite them are congruent. So let's say we have, if AB is congruent to BC, then those angles opposite those sides, which would be opposite of BC would be angle A, is congruent to what's opposite of AB, which is angle C. So what this says is anytime we have an isosceles triangle, those base angles will also be congruent. Now the converse of that, if we take this statement try that again. Copy it, paste it down here. The converse of that says we can take the hypothesis and the conclusion and switch the order. So that becomes if two angles of a triangle are congruent, then the sides opposite them are congruent. Should be the. So that would be if angle A is congruent to angle C, then AB is congruent to BC. So really it goes in either direction. If we have those two, either the sides, then the angles will be congruent, or the angles, then the sides will be congruent. And this will work in any isosceles triangle. Now, let's take that approach. So I have HG is congruent to HK. That are these two sides. Now if those two sides are congruent, I know that the angles opposite them are also congruent. So that would be angle G is congruent to, and I'm not going to say angle K because I wouldn't know which angle I was talking about. I'm going to identify that as HKG. The next one says if angle KHJ, be this angle, and KJH, which would be the other angle, are congruent. Now I'm going to say that the sides are congruent. So the sides opposite them would be HK and JK. Because the angles are congruent, the opposite sides are congruent. And that would be the converse of the base angles theorem. Now we have a couple corollaries to the base angles theorem, and the first one is where we first have our equilateral triangles. So if a triangle is equilateral, then it is equiangular. So all the sides are the same. That tells us all the angles are the same. Just as before, the converse of that says we can switch their order, and we'd say if a triangle is equiangular, then it is equilateral. So if the angles are the same, in this case, the sides are the same. So really, if we have an equilateral triangle, it'll also be equiangular, and the opposite as well. So let's write that as a biconditional statement. Let's say a triangle is equilateral if and only if it is equiangular. So now we can look at some examples. If we look at our triangle PQR, we want to find the angles of it. So by the markings we know it's equilateral, and like we just found, it's also equiangular. So if all the angles are the same, what would each of them be? Well, we know they're the same, so let's say they're all x is their value. I can say that x plus x plus x equals 180 because it is a triangle and the sum of the angles is 180. I could then say 3x equals 180, and therefore x is 60 degrees. So I go back through, and I know each of the angles are 60 degrees. In fact, anytime we have an equilateral or equiangular triangle, each angle will be 60 degrees. Now we go down and look at the bottom example. We need to find x and y. We're probably going to be able to find y first because that's in triangle KLN, and that is an equilateral triangle. Since this side on the KL is 4, we know that y would also be 4, and in fact NL would also be 4. So that gives us our y value. Now we look at triangle NLM, and we have to find x. Well, I know that the angle at N and the angle at M are the same. They're equal or congruent. So their opposite sides are also congruent. So I could say that 4 equals x plus 1 and x equals 3. This example combined the equilateral and the isosceles idea, and we may have to do that to work our way through to find values. Now let's look at a few of the homework problems. If I had AE congruent to DE, as we do in number 3, and I want to see which angles are congruent, I'm going to look at the opposite angles to those sides. And since I'm looking at the whole triangle, that would be angle D and angle A. Let's jump down and look at number 6. For number 6, we have EBC, which is this angle, and ECB. If those are the same, we're going to say the opposite sides are the same. So that would be EB is congruent to EC. If we jump down to number 7, I have an equiangular triangle, so that's also equilateral. So our missing value would be 12. Number 8, if these two angles are 60, the third angle is also 60. It makes it equiangular, which means it's also equilateral. So that would be 16 for our missing value. On number 9, I have that it's equilateral. So all the angles would be equiangular as well, so those would all be 60. Let's look at number 16. So this is an isosceles triangle. What I can first do is use those base angles to find the value of x. So that'd be x plus 7 equals 55. So x would be 48. And then since that angle is 55 altogether, realize x is 48, but it's plus 7, I can do 55 plus 55 plus y equals 180. Give me 110 plus y equals 180. So y would be 70. We would do the same thing on 13. You could set these two values equal, 72 and 9x. And on 12, since the angles are the same, you could set the sides equal.